Imagine it's the early 1830s in America. The nation's first steam locomotives are roaring to life, promising to conquer the vast frontier. But there's a massive catch. These iron behemoths are running on tracks made entirely of wood. Before the Steel Revolution, pioneer routes like the Newcastle to Frenchtown Railroad relied on fragile wooden rails supported by inflexible stone sleepers. Why use flimsy timber to support heavy, fire-breathing machines? It was an era of wild trial, error, and shattered wood, where track technology lagged far behind engine power. Discover why America's earliest trains risked disaster before steel finally forged a nation.
So I want you to just picture this for a second. It is 1833. You are a passenger on one of the very first steam railway lines in the United States, right? It connects the Delaware River down to the Chesapeake Bay. And you've paid a real premium, like 50 cents, for this absolute luxury ride.
Which was a lot of money back then.
Oh, a ton of money. So you're sitting in this wooden carriage and you're being pulled by an imported British steam engine. But here's the catch. It's fueled by American pinewood.
Oh, wow. Pine.
Yeah, pine. Which means it is just spewing this terrifying volcano of sparks and embers directly over your head while you are rocketing through the countryside at the absolute face-melting speed of 30 miles an hour.
Which to them felt like breaking the sound barrier. I mean.
Totally. But as you're coming up to the station, the engineer realizes something completely terrifying. The brakes, they don't really work well enough to actually stop the train.
Of course they don't.
Right. So the engineer cuts the steam, and you're just watching as a group of crew members literally leap off the moving train. They run alongside these massive churning metal wheels, dig their boot heels into the mud, and aggressively thrust a solid wooden fence post right into the iron spokes.
Just to force it to stop.
Yes. Just violently forcing this multi-ton machine to a screeching, throwing everybody forward halt.
I mean, honestly, it's a miracle anyone survived the 1830s.
Yeah.
Really. When we think about modern technology, the jet engine, the smartphone, the bullet train, we have this, this expectation of deliberate, almost pristine design.
Right, like it was all planned out perfectly.
Exactly. We imagine a team of engineers in some brightly lit lab, mapping out the future on a whiteboard, anticipating every single variable, and then just building the perfect machine.
Right.
But early railway history, it completely shatters that illusion. It is the absolute definition of technological muddy waters.
Well, welcome to the deep dive, everybody. Our mission today is to radically change the way you think about railways and, honestly, the way you think about human progress in general. Because ask almost anyone and they will tell you that the railway began with the steam locomotive in the 1800s.
Which is just factually wrong.
Right. So today we are going to uncover the thousands of years of hidden history that came first. Okay, let's unpack this, because what we're looking at today is a story of mechanical walking legs, exploding steam, skyrocketing oat prices, and trains that literally had to be stopped by shoving a fence post into their wheels.
It's a wild ride.
It really is. And to figure out how we got here, we aren't just, reading a textbook. We've pulled together this really incredible stack of sources for you. We're looking at a recent archaeological dig under a Newcastle shipyard, a fascinating local history article on the Wild West of early American rail on the Delmarva Line.
Some really great stuff in there.
Yeah, plus we've got an episode transcript from the Everything Everywhere History podcast, a local news piece from the Northern Echo, and a highly detailed academic paper on the research agenda for the early British Railway.
And what emerges from combining all these disparate sources is this narrative that proves progress is almost never a straight line. The history of the railway isn't just this story of linear technological advancement. It's a story of intense trial, very frequent error, massive economic constraints, and quite frankly, a series of historical accidents that literally dictated the physical dimensions of the modern world.
So to get started, we need to go way back, way before the screaming steam engines and the fence post brakes. If we want to find the true roots, we have to talk about the track itself. Our sources make a massive distinction here, separating the concept of the railway from the train.
Yeah, and that separation is so vital, because the track predates steam power by millennia. I mean, the earliest known track we have actual physical evidence of is called the post track. It's located in the Somerset levels in England.
Okay, so how old are we talking?
The archaeological dating puts this at 3D 838 BC.
Wait, BC?
Yes. We are talking nearly 6,000 years ago.
That is insane.
Yeah.
But I mean, this isn't a metal rail, right? This is essentially a series of wooden planks.
Correct. Yeah, it was built through this wetland marsh. And the underlying physics problem they were trying to solve back then is the exact same problem that modern railways solve today, which is weight distribution and friction reduction.
Right, because of the mud.
Exactly.
Okay.
In a marsh, a heavy cart, or honestly, even just a person walking will sink right into the mud because your downward force is concentrated on a very small area of your feet. So by laying down wooden planks, you distribute that weight over a much larger surface area. It allows safe passage over this really difficult high-friction terrain.
Which, I mean, it sounds like a basic boardwalk. It's the genesis of the idea, like building a specialized, dedicated path to manipulate the environment. But the leap toward our modern concept of a guided track, that really takes shape in ancient Greece, right? I'm looking at the notes here on the Diolkos from the 6th century BC.
Yeah, the Diolkos is this absolute engineering marvel, and it was born purely out of geographical frustration. So the Peloponnese Peninsula in Greece is connected to the mainland by the Isthmus of Corinth.
Okay.
And it's a very narrow strip of land, only about 3.9 miles wide.
Mm-hmm.
But if you were a merchant ship or a navy trying to get around, sailing all the way around that entire peninsula was a long, incredibly treacherous journey. You had storms, you had pirates. It was bad.
So they just wanted a shortcut.
Right. They desperately wanted a shortcut.
But digging a canal with like 6th century BC technology would be an absolute nightmare.
Oh, it was proposed.
Yeah.
They thought about it, but it was physically impossible for them to do it. So they opted for an overland shortcut instead. They built the Diolkos, which was this paved limestone road. But the key is, it wasn't just a flat road.
Right.
They cut 2 parallel, deep physical grooves directly into the stone, so they would pull their actual boats out of the water, hoist them up onto these wheeled carts, and those grooves physically guided the wheels across the landmass.
So the track is actually doing the steering. The grooves act as the rails, physically trapping the vehicle so it can't veer off course.
Exactly. It's guided transit.
And this isn't just some ancient world anomaly that vanished into the dust either. The sources track this concept evolving again heavily by the 16th century. There's this funicular in Austria, the Reichstag, which was used to haul goods up a really steep incline to the Hohensalzburg castle.
Yeah, and what really stands out about the Reichstag is just the longevity of the concept. I mean, it used a rope pulled by animals or sometimes humans to drag these carts up the hill on wooden rails.
Just fighting gravity.
Right. And the sheer mechanical advantage of keeping those wheels on a fixed, smooth wooden path instead of dragging them over a rocky, uneven hillside, that's what made the ascent possible. And amazingly, an updated version of that exact line is still operating today.
Wow, still operating. But moving things up a single, highly specialized castle hill is one thing. To really understand how this technology started to scale, our sources point us underground, right? Like in 1569, German and Austrian miners introduced the system to the Mines Royal in Cumbria, England. It was called the Leitnagel system.
Yes, the Leitnagel system. This is where we really begin to see the true industrial application of guided tracks. So in these subterranean mines, it's dark, it's tight. They laid down parallel wooden planks on the tunnel floor, leaving a very small gap or channel between them.
Okay.
And the wooden mining wagons they used had a projecting pin, that's the Leitnagel, or guide nail sticking straight out of the bottom.
Wait, so there's a pin sticking out of the bottom of the cart and it drops into the gap between the floor planks.
Exactly.
That sounds exactly like the underlying mechanics of a slot car racing track, like those little toys where the pin keeps the car locked into the groove so it doesn't just fly off on the corners. Is that the exact same physics at play here?
It is the exact same principle. That pin keeps the wagon centered so the wheels stay perfectly on the smooth wooden planks. I mean, think about a dark, cramped, muddy mine shaft. This was revolutionary.
All right, man.
A single miner could push a significantly heavier cart in the pitch black without worrying about the cart drifting into the rock walls or getting bogged down in the uneven dirt.
But, okay, if this friction-reducing guided technology was so brilliant, why did it stay buried in the dark? Why didn't they immediately just, I don't know, pave the streets of London with wooden tracks and guide pins?
Well, it all comes down to environmental control. When you're underground, you control the gradient. You are the one digging the tunnel, so you can make it perfectly level or you can maintain a very slight deliberate decline.
Ah, right.
Above ground, the topography is chaotic. You have hills, valleys, rain, and mud. A wooden track exposed to the British weather rots very, very quickly. But more fundamentally, early modern economies just didn't have a product heavy enough in a volume large enough. to justify the immense capital expenditure of leveling the land to build above-ground railways.
Right, until they found something they desperately needed millions of tons of. Coal.
Precisely. Coal changes everything.
Yeah.
The British coal boom in the 17th and 18th centuries provided this massive economic forcing function. The mines were suddenly producing way more coal than horses could physically pull in traditional wagons over these deeply rutted, muddy dirt roads down to the rivers.
So the whole supply chain is just bottlenecking.
Exactly. They had to figure out a way to scale that underground wooden rail technology to the surface.
And this brings us to this really incredible discovery that gives us a physical window right into that era. Because in 2013, archaeologists were excavating the site of the old Neptune shipyard in Newcastle upon Tyne. They were trying to clear the area for modern development, right? And they were actually hoping to find Roman ruins, given the proximity to Hadrian's Wall. But instead, they hit something completely different. They unearthed a perfectly preserved 25-meter stretch of an 18th century wooden railway from the 1760s, the Willington Wagonway.
What's fascinating here is just the sheer luck of this preservation. It cannot be overstated. As the piece in the Northern Echo details, wood from the 1760s should have completely decomposed. It should be gone.
Right. It's organic material.
Exactly. The only reason it survived is because it was buried beneath shipyard waste in a deeply waterlogged anaerobic environment.
Anaerobic meaning no oxygen, right? So the bacteria that normally eats wood just couldn't survive in that mud.
You've got it. It was completely sealed in time. But of course, that created an immediate crisis for the modern curators at the National Railway Museum. Because the moment those archaeologists pulled that wood out of the mud and exposed it to the air, the clock started ticking.
Oh, because now there's oxygen.
Right. Oxygen meant rapid deterioration. They had to intervene immediately using specialized chemical treatments to replace the water and the cellular structure of the wood before it weathered, dried out, and literally just crumbled to dust right in front of them.
Which is such a massive win for history because studying those 25 meters of track revealed an astonishing level of engineering. Like, these wagonways were built to carry chaldrons, these massive wooden wagons from the inland collieries down to the River Tyne.
And we really have to look closely at the math of why they built them. It is all about the multiplier effect of reducing rolling resistance.
Okay, break that down for us.
Sure. So a horse pulling a cart on a typical 18th century dirt road was fighting immense friction. The wheels sink into the dirt, meaning the horse is constantly having to pull the cart up and out of its own rut just to move forward.
So by putting smooth wooden wheels on smooth wooden rails, they eliminate the rut completely.
Yes. They drastically reduce the rolling resistance. Historical records show that on these wooden wagonways, a single horse could comfortably pull 10 to 13 long tons of coal per trip.
Wait, 13 tons for one single horse?
Yes. That is roughly 4 times more weight than the exact same animal could pull on a regular dirt road.
That is wild.
Right. They quadrupled their logistical output without adding a single extra horse to their workforce. But sustaining that kind of immense weight on timber requires some truly brilliant structural design. And the Willington dig revealed they used a double wooden rail system.
Well, yeah, because if you just lay a plank of wood on the ground and run a 13-ton cart over it every day, that wood is going to splinter into a million pieces.
Inevitably, it would be destroyed in a week.
Yeah.
So what they did was lay a foundational wooden track, and then they pegged a second sacrificial wooden rail directly on top of it.
Oh, wow. That is really smart. It's modular. Like when the top rail gets chewed up by the heavy wagon wheels, you just pop out the wooden pegs, throw away the damaged top rail, and peg down a new one. You don't have to excavate the entire foundation of the track.
Exactly. It shows a really deep understanding of maintenance cycles. But the most ingenious feature they unearthed was something called a dip pond loop.
A dip pond?
Yeah. The main track actually diverted and ran down into a shallow man-made pond. They intentionally drove the heavy wooden coal wagons right into the water.
See, okay, why would you want your heavy wooden machinery soaked? That feels counterintuitive.
It does, but it's all because of the friction. As the massive wooden wheels rolled along the wooden rails, the friction generated immense heat. Combined with the summer sun, the wood of the wheels would dry out, shrink, and become highly brittle.
Ah.
And if a wheel cracked under a 13-ton load, it was catastrophic.
Oh.
Whole operation stops. So the dip pond acted as a hydration station. Immersing the wheels in water caused the wood to swell up, tightening the joints and keeping the wood supple so it wouldn't shatter.
But here's the detail that completely won me over when I read this. They realized that while the wooden wheels needed to be soaked, the horse pulling the wagon could not be standing in water all day or its hooves would rot.
Right. Hoof rot was a serious issue.
So right through the middle of this shallow pond, they built a raised, dry stone path. The wagon wheels drop into the water on the sides, but the horse walks high and dry down the center. I mean, that is systemic, empathetic engineering.
It really is a masterclass in solving cascading problems.
Yeah.
You solve the friction problem with wooden rails. The heavy loads on those rails create a drying problem for the wheels. You solve that with a pond. The pond creates a hoof rot problem for the horses.
Yeah.
So you solve that with a raised stone path. It's brilliant.
It's so clever. And I want to pause here just for a second because I think it is really easy for us to hear wooden rails and just picture like a little mine cart in a backyard. But these wagonways were landscape-altering mega projects. To make the system work smoothly, they couldn't just follow the natural rolling hills of the English countryside. The carts were way too heavy for a horse to pull uphill. They had to rely on gravity.
Yes. The entire route had to be a continuous, gentle, downward slope from the mine all the way to the river.
Which means they are acting exactly like Roman aqueducts. They're building massive timber embankments over valleys and carving deep cuttings through hills just to maintain a 1-degree downward gradient for miles. I mean, imagine the capital investment here. They are essentially building an interstate highway system entirely out of oak and fir.
It fundamentally reshaped the economic geography of the northeast of England. But, wood simply hit its physical limit. As demand for coal continued to skyrocket, the mine owners wanted to move more coal faster.
Naturally.
So they increased the weight of the chaldrons. And under that immense pounding pressure, even the double-laid, water-swollen oak rails began to warp, splinter, and fail.
Oh.
The constant maintenance costs began to completely eat the profits.
So the entire Industrial Revolution is about to bottleneck because they literally cannot physically move the fuel fast enough. They need a material that has the smoothness of wood or stone, but the tensile strength to not shatter under immense repetitive pressure.
They needed iron. And this ushers in a really fascinating era of metallurgical transition. In 1760, the Coalbrookdale Iron Works started experimenting. They took thin plates of cast iron and just nailed them directly onto the tops of the wooden rails.
Just giving the wood an iron armor to stop the splintering.
Exactly. But by 1767, they realized, wait, we could just cast the entire rail out of solid iron. And the moment they do this, we see the eruption of what I can only describe as the ultimate 18th century tech format war.
Yes, like VHS versus Betamax, or Apple's Lightning Cable versus USB-C. Because once you switch to iron, you have to decide exactly what shape the track should be. And our sources highlight two fiercely competing systems here. Plateways versus edgeways. Walk us through this divergence.
So in 1787, a colliery manager named John Kerr developed the plate rail. This was an L-shaped cast iron rail. Think of it kind of like a metal gutter. The vertical part of the L acted as a built-in wall, a flange.
So the track itself has a raised lip.
Yes. Because the track has the lip, the wagons didn't need specialized wheels at all. You could just use a standard road wagon with flat wooden wheels. The wheel rolls on the flat part of the L, and the vertical metal wall stops it from sliding off the track.
I mean, this sounds incredibly practical. If I am a merchant, I can use my horse to pull a standard cart down a dirt road, pull it straight onto this plateway for the low-friction long haul, and then pull it right back off onto the cobblestones when I get to the city. It is fully intermodal. I never have to unload the coal.
The flexibility of the plateway was a massive selling point, absolutely. And entire regions, like South Wales, adopted it really aggressively. But 2 years later, in 1789, William Jessup introduced the competitor, the edge rail. And this was a completely flat, narrow piece of iron. It had no raised lip whatsoever.
Oh, how on earth does the cart stay on?
Jessup moved the flange. Instead of putting the lip on the track, he cast a metal lip directly onto the inside edge of the wagon's wheel.
Okay, so the wheel has the lip, not the track. Why does this become such a vicious format war, though? Like, if the plateway lets you use literally any cart you want, why would anyone use Jessup's edge rail?
Because of dirt, physics, and friction. John Kerr's L-shaped plate rail had a fatal flaw. Because it was shaped like a gutter, it acted like a gutter. It collected mud, rocks, leaves, and debris from the horses walking beside it.
Oh. And as that debris builds up on the iron,
the friction increases dramatically. The smooth iron gets covered in gritty mud, completely defeating the whole purpose of the railway. Even worse, if a large enough rock fell into the corner of that L, a heavy, fast-moving coal cart would hit it and violently derail.
That's a huge problem.
Right. Jessup's flat edge rails, however, were inherently self-cleaning. Because the rail was narrow and elevated, dirt and rock simply fell off the sides.
So the edge rail gives you peak mechanical efficiency and cleanliness. But the trade-off is massive, isn't it? If you put a flange on the wheel of a cart, that cart can only ever roll on a track. If you try to pull a flanged wheel onto a regular dirt road, that metal lip is going to dig into the mud like a plow blade, and the cart will get instantly stuck.
Exactly. You are committing to a closed system. The vehicle lives on the track and nowhere else. This meant that colliery owners who chose the edgeway had to build expensive transshipment hubs. They had to manually shovel the coal out of the track-bound carts and into riverboats or road wagons at the end of the line.
It is the eternal engineering debate, right? Ultimate convenience versus ultimate efficiency. And looking at the world today, we know efficiency won. The edgeway, with the flat track and the flanged wheel, is the standard for every modern train on Earth. But shifting from wood to iron wasn't a perfect transition out of the gate, was it? Early iron had some serious structural flaws.
Major flaws. The early rails were made of cast iron. Cast iron is made by pouring molten iron, which has a very high carbon content, directly into a sand mold.
It's incredibly hard, yes, but that high carbon content makes its internal structure crystalline.
Meaning it is brittle, like glass. Exactly like glass. It is extremely strong under compression if you just push straight down on it, but it is terribly weak under tension or bending forces. Because it was so brittle, they could only successfully cast these rails in very short lengths, usually about 3 feet long.
3 feet, which means every 3 feet you have a joint, a gap.
A bump. Imagine riding a heavy, unsuspended cart over a seam every 3 feet.
Clickety-clack, clickety-clack.
Right. It was unstable, it was loud, and it was jarring, which only increased the stress on the brittle iron, causing it to shatter constantly. It wasn't until 1820 that an engineer named John Birkinshaw completely revolutionized the material. He patented a method for rolling wrought iron rails.
Okay, so what makes wrought iron different from cast iron? Why doesn't it shatter?
Wrought iron is made through a process called puddling. You actually stir the molten iron to burn off much of the carbon, and then you physically hammer and roll it. This process removes the impurities, the slag, and it actually stretches the metal, giving it a fibrous grain, almost like wood.
So instead of a rigid crystal that snaps under pressure, you have a fibrous metal that has a slight amount of flex to it.
Precisely. It is much tougher.
Okay.
Because it could flex without breaking, Birkinshaw was able to roll these wrought iron rails into 18-foot lengths.
Huge upgrade.
Massive. He also shaped them into a T-profile, which maximized structural strength while minimizing the amount of heavy iron required.
And this shift to 18-foot wrought iron rails inadvertently changes the course of human history, because once you have a track that long and that strong, you finally have a foundation capable of supporting something infinitely heavier than a wooden wagon and a horse. It is the literal runway for the steam engine.
It is the missing piece of the puzzle. Which brings us to the actual explosive birth of the steam locomotive. And we really have to start with an absolute maverick of engineering here. Richard Trevithick. Trevithick was a pioneer of high-pressure steam engines. In 1804 in Wales, he decided to put one of his high-pressure boilers on wheels. He called it the Penydarren.
The first true railway steam locomotive.
Mechanically, it was a total triumph. During its demonstration, it successfully hauled 10 tons of iron, 5 wagons, and 70 men at a speed of about 5 miles per hour. It proved that a steam engine could physically move itself and a massive payload.
But practically?
Practically, it was a disaster. Trevithick's engine was unimaginably heavy. And remember, this is 1804. They were still using those brittle 3-foot cast iron rails. The immense pounding weight of the Penydarren completely shattered the tracks beneath it.
Oh, no.
The ironworks owners who sponsored him basically said, look, this is a great parlor trick, but we cannot afford to replace our shattered railway every time you run this machine. They converted his locomotive into a stationary pump and completely abandoned the idea.
But Trevithick doesn't give up. Like 4 years later, in 1808, he goes to London. He sets up a circular demonstration track in a field and builds a new locomotive called Catch Me Who Can.
Great name.
Great name. And he charges the public a shilling just to ride it, like a carnival attraction. And what happens? The exact same thing. The weight of the engine breaks the rails, it derails, and Trevithick goes bankrupt.
He was a visionary, but he was operating just ahead of the material science of his time. He needed the wrought iron that wouldn't be invented for another 12 years.
This raises a massive question for me, though. If these giant, hissing, fire-breathing metal monsters just kept violently destroying the multi-million-dollar track infrastructure, Why didn't the industry just ban them? I mean, why did anyone keep throwing money at steam engines when a horse worked perfectly well without shattering the iron?
This is where we see macroeconomics forcing technological evolution. If we connect this to the bigger picture, the answer is war, specifically the Napoleonic Wars. During the early 1800s, Britain was locked in a massive conflict with France. Napoleon instituted the continental system, essentially blockading British trade with Europe. At the same time, Britain was fielding massive armies and navies.
Meaning the military is buying up every available horse.
It created a severe domestic shortage of horses, yes. But the cascading effect was even worse. Because trade was blocked, the supply of grain was restricted, the price of oats, the literal fuel for the horses, skyrocketed. During the wars, the price of horse feed increased by 50%, and in some areas much more.
Oh, wow. So the steam locomotive wasn't adopted because some genius thought it was faster or sleeker. It was adopted out of sheer desperation. The biological fuel oats had become unsustainably expensive. They were being priced out of using horses. The locomotive is basically an economic refugee from horseflation.
It is the ultimate forcing function. They had to make steam work. But there was another massive intellectual hurdle holding them back: the smooth wheel problem.
Right, our sources mention this deep skepticism. Even brilliant engineers genuinely believed that a smooth iron wheel on a smooth iron track would simply spin in place.
They just couldn't wrap their heads around the physics of adhesion. Because friction had been their enemy for thousands of years, they overcorrected. They assumed that without the rough texture of a dirt road, the metal wheel wouldn't be able to grip the rail tightly enough to pull a heavy load.
So they thought it would just be like a car on ice.
Exactly. They figured Trevithick only got away with it because his engine was so absurdly heavy that the sheer weight forced the grip. But of course, that weight broke the rails.
So they think, okay, we need a lighter engine so we don't break the tracks, but if it's lighter, the wheels will just spin. How did they try to solve this?
With some wildly creative and bizarre mechanical detours. In 1812, an engineer named John Blenkinsop, working with Matthew Murray, built a locomotive called the Salamanca. To solve the grip problem without adding weight, they invented the rack-and-pinion system. They laid a special rail that had teeth on the side of it, a rack, and the locomotive had a giant toothed cogwheel that slotted into those teeth, physically pulling the engine forward, gear by gear.
Okay, that makes logical sense. It is like a roller coaster on the big climb. But the next attempt, here's where it gets really interesting because it shows how incredibly hard it is for human beings to let go of biological paradigms when we are designing new technology.
You were talking about William Brunton.
Yes. Humans were so deeply conditioned by thousands of years of watching animals. Watching a horse push backward against the earth with its legs to propel itself forward. We thought that was the only way locomotion worked. So in 1813, William Brunton patents a steam engine that literally has mechanical legs.
A mechanical traveler.
It had these two long metal legs attached to the back of the boiler. They were driven by steam cylinders. One leg would lift up, plant a mechanical foot onto the ground between the rails, and push backward, propelling the whole train forward. Then the other leg would do the same. I want you to imagine a giant, hissing, smoke-belching iron cylinder trying to awkwardly walk down a track like an enormous metal grasshopper.
It sounds absurd to a modern listener, but it perfectly illustrates the psychological barrier of the era. We try to map the old, familiar ways of doing things onto terrifying new technologies. Brunton couldn't trust the wheel, so he replicated the horse. And the tragic part is, the mechanical legs actually worked. The machine successfully walked at about 2.5 miles an hour.
Until it exploded.
Yes. In 1815, during a demonstration, Brunton pushed the boiler pressure too high to show off to a crowd, and it catastrophically exploded, killing over a dozen people. It was a horrific reminder of how volatile high-pressure steam was.
But all of these weird, wonderful, and deadly experiments were the necessary trial and error required to break the mental models, right? And the synthesis of all these ideas finally happens at a colliery in Wylam.
Wylam is where the pieces click into place. The manager there, William Headley, and his foreman, Timothy Hackworth, conducted a series of experiments and proved definitively that smooth wheels did have enough adhesion on smooth rails, provided the weight was managed correctly. They didn't need cogs, and they didn't need walking legs.
They just needed better chassis design, because in 1813, they built a famous locomotive called Puffing Billy. But how did they stop Puffing Billy from shattering the brittle tracks like Trevithick's engines did?
Weight distribution. Instead of putting all the weight of the massive boiler onto 4 wheels, they designed 2 separate 4-wheeled trucks, or bogies. They placed the locomotive on top of these, giving it 8 wheels in total.
Ah, so you are taking the same 5-ton boiler, but you are spreading that immense downward force over twice as many contact points on the brittle iron rail. The load per wheel drops, and the track survives.
Exactly. It was a crucial breakthrough. But the man who would take all of these disparate pieces, the smooth wheels, the weight distribution, the wrought iron rails, the high-pressure steam, and forge them into the modern railway was George Stephenson.
George Stephenson's origin story is completely wild. He wasn't some wealthy aristocrat educated at Oxford who decided to tinker in a pristine lab. He was born into absolute poverty in the northeast of England. He was an illiterate coal picker. He literally started his working life as a small child, picking stones and debris out of the coal piles.
But he was deeply observant and endlessly curious. As a teenager, he was put in charge of running the stationary steam engines that pump floodwater out of the mine shafts. In his spare time, he would take these massive, complex engines completely apart and put them back together just to understand the mechanics of how they breathed.
He didn't even learn to read or write until he was 18 years old. He paid for night school out of his meager wages, specifically so he could read engineering texts. By his 20s, he had earned a reputation as an engine doctor, the guy you called when a massive industrial machine broke down and no one else could figure out why.
And in 1814, he builds his first locomotive at the Killingworth Colliery. He named it Blücher, after the Prussian general who had recently helped defeat Napoleon.
Blücher. Cue the terrified horse whinny right here.
Yeah, insert horse noise.
Yeah.
But beyond the cinematic name, Stephenson introduced a monumental engineering upgrade with Blücher and his subsequent engines. It was called the steam blast.
Okay, explain how that works, because this seems like the moment the steam engine becomes truly self-sustaining.
In the earliest steam locomotives, once the steam pushed the piston inside the cylinder, the spent steam was simply vented out the side of the engine into the open air. It made a deafening, terrifying hiss that panicked local horses. Stephenson realized this was a massive waste of energy. He took that exhaust pipe and redirected it so it pointed straight up into the smokestack.
Okay, let me get this straight. He shoots the highly pressurized exhaust steam up the chimney. As it blasts upward, it creates a vacuum behind it.
Exactly. It creates an intense draft. That vacuum pulls fresh air violently through the firebox at the bottom of the boiler.
It is acting exactly like a blacksmith's bellows. It is a self-regulating feedback loop. The faster the train goes, the more pistons fire. The more pistons fire, the more steam blasts up the chimney. The more steam blasts up the chimney, the harder it pulls oxygen into the firebox. The fire burns hotter, which boils the water faster, which creates more steam.
It vastly increased the power output and efficiency of the locomotive. And Stephenson's relentless optimization over the next decade led him and his brilliant son Robert to the absolute defining moment in railway history. The Rainhill Trials of 1829.
Set the scene for us. Why were the Rainhill Trials happening?
A group of ambitious investors was building the Liverpool and Manchester Railway. This was intended to be a marvel of the modern world. But as they were laying the tracks, they still hadn't decided how they were going to move the trains. The board of directors was split. Half of them wanted to use moving steam locomotives. The other half thought moving engines were too unreliable and dangerous.
So what did they want to do?
They wanted to use stationary steam engines placed every few miles along the track, which would just pull the passenger cars along with giant ropes.
Rope-pulled trains between major cities. Incredible.
To settle the debate, they decided to host an open public competition at Rainhill. They offered a massive 500-pound prize, a fortune at the time, for the best locomotive design. The engine had to consume its own smoke, pull a specific weight, and reach a minimum speed of 10 miles per hour.
It was the space race of the 1820s. George and Robert Stephenson entered a locomotive they called the Rocket, and the Rocket featured another massive leap forward in thermodynamics, the multi-tubular boiler.
This is a brilliant piece of thermal engineering. In older engines like Trevithick's, the boiler was essentially a giant tank of water with one large pipe, or flue, running through it. The fire was at one end, the hot gases traveled through that single pipe, and the heat transferred to the water to make steam. But it was inefficient. Most of the heat just escaped out the chimney before it could boil the water.
So how did the Stephensons fix that?
Surface area. Instead of one big pipe, the Rocket used 25 narrow copper tubes running right through the water tank.
Ah. By dividing the hot gases into 25 smaller streams, you exponentially increase the amount of hot metal that is physically touching the water. More surface area means the heat transfers much faster, allowing the engine to generate high-pressure steam continuously rather than constantly running out of breath.
Exactly. When the Rocket hit the track at Rainhill, it didn't just win, it completely obliterated the competition. During the trials, it reached an absolutely unheard of speed of 30 miles per hour.
30 miles an hour.
The investors were stunned, the debate was over, moving steam locomotives were the future, and in 1830, the Liverpool and Manchester Railway opened.
And we really have to emphasize what a paradigm shift this was. Before 1830, railways were almost entirely private industrial tools. They were grimy tracks used to move coal from a private mine to a river. The Liverpool and Manchester was the first fully timetabled, entirely steam-powered, double-track, intercity passenger railway in the world. It is the moment the railway stopped being a mining tool and became public mass transit.
And it was terrifying for the public.
Yeah.
You have to put yourself in the mindset of someone living in 1830. Prior to this moment, the absolute fastest a human being had ever traveled in the history of the world was on the back of a galloping horse.
Which is what, maybe 25, 30 miles an hour for a very short, exhausting sprint?
Exactly. And now you have this massive, screaming, smoke-billowing iron behemoth maintaining 30 miles an hour continuously for hours. Critics were horrified. Prominent voices in Woolwich famously wrote that they would sooner let themselves be fired out of a military rocket than trust themselves to travel at the insane speed of 18 miles an hour on a train.
They genuinely believed the physics would kill them, right? That the human body might asphyxiate because the air would be sucked out of their lungs, or that the slightest bump on the iron rails would shatter the entire train like glass.
The fear was visceral. But the economic reality of moving goods and people that fast completely overwhelmed the fear. The technology exploded. And while the British were busy perfecting the heavy engineering, laying robust wrought iron tracks, and building massive stone viaducts, the technology was making its way across the Atlantic. And in America, they were figuring out how to run these new machines in a completely different, far more chaotic environment.
Which brings us back to that terrifying story from our hook, the American Wild West of early rail. Because America was massive, largely unmapped, and desperate for connectivity. One of the earliest passenger lines was the Newcastle to Frenchtown Railroad in Delaware and Maryland, which opened its steam line in 1833.
The American approach was fascinating because they lacked the established heavy industry of Britain. So for this line, they literally imported a Stephenson locomotive from England. They shipped it across the Atlantic piece by piece and reassembled it in Delaware.
But they didn't have the same fuel. Newcastle in England was literally built on high-grade coal. The American East Coast had endless forests, so they decided to fuel this highly tuned British coal engine with American Pinewood.
Which burns completely differently. Pine pops and throws massive embers.
Exactly. When they fired it up, it threw huge flaming embers out of the smokestack, raining fire down onto the open passenger carriages. People's clothes were catching on fire. But the engine could hit that magic 30 miles per hour.
It could hit it in theory, but the actual reality of operating these novel machines was often a comedy of errors. Our sources highlight the inaugural trip of that imported locomotive. The distance between Newcastle and Frenchtown was only about 17 miles. At a top speed of 30 miles an hour, the journey should have taken roughly an hour.
Instead, it took 15 hours. Because they forgot the most fundamental component of a steam engine. They fired up the boiler, got all the local politicians and VIPs on board, chugged down the track, and abruptly stopped. They ran out of steam. Literally. Because no one had thought to bring extra water.
The logistics of a mobile boiler hadn't been fully mapped out.
So the crew had to stop the train, grab wooden buckets, and run into the woods looking for creeks, streams, and mud puddles. They had to run back and forth, scooping up whatever water they could find, and dump it into the boiler just to move a few more miles down the track. It is spectacular trial and error.
But as you mentioned at the beginning, even more wild than how they kept it going was how they stopped it. Early braking technology was virtually non-existent. On the British locomotives like the Rocket, there were no brakes on the wheels at all. The driver just had to expertly throw the engine's valves into reverse and hope the immense mechanical strain didn't blow the cylinders apart.
But on the Delmarva line, they developed the roustabout method. The train approaches the station, the steam is cut, but a multi-ton iron machine has incredible forward momentum. So the crew members physically jump off the train, run alongside the wheels, and jam a wooden fence post right into the heavy iron spokes to force it to stop. The bravery or the sheer lunacy of those workers is astounding.
It is astonishing that the casualty rate wasn't higher, but it deeply reflects the ad hoc, rapid prototyping environment of early American rail. They were solving life and death physical problems in real time. And this specific line also gave us some enduring cultural terminology.
Right. To manage a single track and avoid head-on collisions at 30 miles an hour, they desperately needed a signaling system. But this is the 1830s. The telegraph hasn't been invented yet. You can't just call the next station.
So they relied on optics. Station agents would climb up on platforms and use telescopes to peer miles down the long, straight tracks. If they saw a train approaching in the distance, and they knew the track ahead was clear of any broken-down trains or debris, they would hoist a large white canvas ball to the very top of a tall pole outside the station.
A high ball.
Exactly. When the train's engineer looked through his own spyglass and saw the white ball at the top of the pole, he knew he had permission to proceed at maximum speed without stopping. This birthed the railroad slang highballing, which eventually bled into general English to mean moving fast, rushing, or leaving quickly.
It's amazing how much of our modern world is just leftover railroad jargon. But behind all these wild stories of fence post breaks and bucket brigades, a massive, fundamental shift in human economic thinking was taking place. You mentioned earlier how long it took humans to realize speed was an asset. Let's dig into the physics of that.
This is what economic historians call the doctrine of speed. For all of recorded human history, transportation efficiency was a function of mass, not velocity. If you wanted to move goods efficiently, you put a massive load on a river barge or a canal boat, and you pulled it very, very slowly with a horse.
Because speed was biologically expensive.
Extremely. An 1824 article in the Mechanics magazine finally articulated the mathematics that broke this thousands of years old paradigm. The article explained the physical limits of biological power. If a horse is pulling a boat on a canal at 2.5 miles per hour, it can pull an enormous amount of weight. But as you force that horse to walk faster, more and more of its metabolic energy is consumed just trying to move its own heavy body weight.
Yeah, right. By the time a horse is running at 12 miles an hour, 100% of its energy is being used just to keep its legs moving at that speed. Its actual pulling power drops to absolute zero. You can't pull a heavy barge with a sprinting horse.
And then you have the physics of the water itself.
Hold on. You are losing me here. I get why the horse gets tired, but why does the water matter? If I push a boat faster, doesn't it just glide easier once it gets going?
No, it is actually the opposite. In fluid dynamics, water resistance increases exponentially with speed. As a canal boat moves faster, it pushes water out of the way, creating a bow wave in front of it. To go faster, the boat essentially has to try and climb up its own waves. The faster you try to pull it, the harder the water violently pushes back. It requires an exponential increase in energy for a marginal increase in speed.
Oh, okay, so a fast boat requires exponentially more energy, but a fast train.
A fast train faces almost zero rolling resistance. A smooth steel wheel on a smooth steel rail does not deform. It doesn't create a wave. The Mechanics magazine article pointed out that while wind resistance increases slightly, rolling friction remains incredibly low regardless of how fast you go.
So the math completely flips. At 2.5 miles per hour, a horse on a canal is economically efficient. But once you cross the threshold of about 13.5 miles per hour, the biological and fluid dynamics fail, and the steam locomotive utterly obliterates the canal's efficiency.
Exactly. You can move the same amount of heavy cargo in a fraction of the time. This allows a merchant to make 10 round trips for every one trip the canal boat makes.
They realized the railway could, as the visionaries of the time said, annihilate space and time. If you can move fresh milk from a farm deep in the countryside into the heart of London or New York before it spoils, you haven't just improved transportation. You have literally created entirely new economic markets that physically could not exist yesterday. You've reshaped the diet, the geography, and the daily schedule of humanity.
But there is a catch. To make these incredible speeds safe, and to link all these disparate experimental little rail lines into a cohesive, space-annihilating global network, the world had to agree on some basic ground rules. You can't have a network if the trains from New York cannot physically fit on the tracks in Philadelphia.
And this brings us to one of the most consequential and arguably absurd historical accidents in modern history: the lock-in of the standard gauge.
So we know that in the early days of the wagonways, every colliery and every mine just built whatever track width they felt like. The gauge, the distance between the two inner edges of the iron rails, varied wildly. Some tracks were 3 feet 10 inches wide, some were over 5 feet wide. There was zero standardization.
But then George Stephenson emerges as the dominant force in early railway engineering. Because he is the preeminent expert, he is hired to essentially design and build the massive Stockton and Darlington Railway in 1825, and then the famous Liverpool and Manchester. When it came time to lay the tracks for these foundational lines, Stephenson needed to pick a gauge. And what did he choose? 4 feet, 8.5 inches.
Which is such an oddly specific, clunky number.
Right. 4 feet 8.5 inches wide. Was this carefully calculated for optimal steam distribution? Did he figure out the exact mathematical balance of gravity, lateral force, and wind resistance for a 5-ton boiler navigating a turn?
Not at all. He chose 4 feet 8.5 inches simply because he was most familiar with it. It was the exact gauge used at the Willington Wagonway in Newcastle. The very same horse-drawn coal track from the 1760s that archaeologists dug out of the mud in 2013. The same track where Stephenson had worked as a young, illiterate brakesman. He literally just copy-pasted the dimensions of an 18th century horse cart track onto the world's first intercity steam railways.
It is the ultimate historical accident. And because Stephenson's early lines were so wildly successful, other engineers building connecting lines nearby used the exact same gauge so their trains could seamlessly roll onto his tracks.
And because Britain was the dominant global economic empire of the 19th century, when they exported their locomotives, their iron rails, and their engineers to Europe, to the Americas, and to the colonies, they inherently exported Stephenson's 4-foot 8.5-inch gauge. Today, 70% of the world's railways use this exact standard gauge.
It is a massive lock-in effect. It is exactly like modern software monopolies. Think about the QWERTY keyboard on your laptop. Is it the most efficient way to type? No, it was designed to slow down mechanical typewriters so the keys wouldn't jam, but once everyone learned it, it became impossible to change.
The network effect makes switching too costly. And what's truly ironic is that later in his life, even George Stephenson admitted it was a mistake. When younger engineers asked him if he would do it differently, he confessed that if he could start over, he would make the gauge wider, maybe by a few inches.
Because 4 feet 8.5 inches was too restrictive?
Yes. As locomotives became vastly more powerful, they needed wider boilers and larger fireboxes. But they were physically constrained by the width of the wheels, which were constrained by the track.
Which means we were stuck. I'm looking at Isambard Kingdom Brunel, the brilliant engineer of the Great Western Railway in Britain. He realized Stephenson's gauge was too narrow, so he built his tracks to a broad gauge of 7 feet and a quarter inch.
Brunel's broad gauge was mathematically and mechanically superior in every way. It allowed for a much lower center of gravity, which meant you could build massive, powerful engines with enormous driving wheels. It provided an incredibly smooth, fast ride with far less risk of derailment.
Why didn't Brunel win? If it was objectively better tech, why are we still on Stephenson's narrow gauge?
Because Stephenson got to the market first and established the network effect. Brunel's trains couldn't run on Stephenson's tracks, and vice versa. Where the two networks met, passengers had to get off one train, walk across a platform, and get on another. Freight had to be manually unloaded and reloaded. It was an economic bottleneck. Eventually, the British Parliament stepped in and mandated Stephenson's narrow gauge just to force interoperability and efficiency. Brunel's superior technology was ripped out of the ground.
It forces us to ask a profound question about the physical world we inhabit. Consider the cascading effects of that single arbitrary decision by George Stephenson. The width of the railway dictated the maximum width of the trains. The width of the trains dictated the width of the tunnels they had to bore through solid mountains, and the width of the bridges they built over rivers.
It creates an invisible cage for future innovation. When we invented the standardized intermodal shipping container in the 20th century to revolutionize global shipping, its maximum dimensions were heavily constrained by the fact that it had to fit on a standard gauge flatbed rail car.
The experts in our academic sources take this to an even more mind-bending conclusion. They argue that even modern space exploration is constrained by the Willington Wagonway. The solid rocket boosters for the space shuttle were built by Morton Thiokol in Utah, but they had to be transported to Florida for launch. Because of their weight, they had to go by train, which meant they had to fit through train tunnels in the Rocky Mountains, tunnels that were bored over a century ago, just wide enough to accommodate trains running on tracks that are 4 feet 8.5 inches wide.
Is it possible that the dimensions of humanity's most advanced spacefaring hardware were ultimately dictated by the arbitrary width of an 18th century horse-drawn coal cart? It is highly probable.
That is staggering.
The railway wasn't just a piece of technology. It was a physical framework that we bolted the rest of the modern world onto. Even the seemingly mundane details of how we run our complex logistical infrastructure today were solved by those early engineers. Our academic sources point out that the concept of containerization, putting freight in standardized modular boxes to easily transfer from a rail car to a canal boat, was being tested at collieries as early as 1788.
Long before the steam engine. And the railway switch, the mechanism that allows a fast-moving train to divert from one track to another without stopping.
Invented by John Kerr in 1797.
The same guy who invented the L-shaped plate rail. Even the iconic clickety-clack sound of the train, which was caused by the wheels hitting those tiny gaps between the short lengths of iron rail expanding and contracting, was eventually solved. Today, we use continuously welded rails that stretch for miles. We swapped out wooden ties for concrete to handle the immense downward force of high-speed bullet trains. We started banking the curves of the tracks, tilting them inward just like a NASCAR speedway, so that centrifugal force doesn't throw a 200-mile-per-hour train off into the woods.
Every single piece of modern rail transport, from the magnetic levitation trains in Japan to the massive freight networks of North America, is just a highly polished iteration of 18th century miners trying to figure out how to keep their wooden carts from sinking into the mud.
It is a phenomenal journey. We started today's deep dive looking for the pristine lab of deliberate invention, and instead we found a glorious, muddy, chaotic mess. We traced the modern railway back from the space shuttle boosters, past George Stephenson's rocket, past the mechanical walking legs and the rack-and-pinion gears. We traced it past the skyrocketing oat prices of the Napoleonic Wars, back to the cast-iron edgeways, the wooden dip ponds of Newcastle, the Austrian castles, and all the way back to the stone grooves of ancient Greece.
It is a vital reminder. Every time you look at a seamless global supply chain delivering goods to your door, or every time you board a transit train to go to work, you are quite literally riding on the legacy of desperate, brilliant miners who just wanted an easier way to move heavy rocks in the rain. Progress is messy, it is highly reactive to external shocks, and it is profoundly beautifully human.
And that leaves us with one final, deeply provocative thought for you to mull over as we wrap up this deep dive. We spent centuries trying to design machines that mimicked biology. We built literal steam trains with mechanical walking legs because we couldn't let go of the idea of the horse. It took decades of explosive failure to realize that the machine didn't need to be a better horse. It needed its own entirely new environment, the smooth iron rail, to reach its true world-changing potential.
The physical environment had to change to accommodate the new power source.
Exactly. Look around at the artificial intelligence and the groundbreaking new technologies we are building today. Are we still just trying to build mechanical horses? Are we forcing new tech to operate within our old biological, human-centric workflows? Or are we going to realize that to see what this new technology can truly do, we need to stop building metal horses and start building entirely new tracks?
A fascinating question. The pristine lab is a myth, but the muddy reality is where the future is actually forged.
Thanks for joining us on this deep dive. We'll see you next time.